Three, two, one, and here we go. The last content video for Math 2070 online. And today we're going to wrap up the course material by revisiting diagonalization, and specifically diagonalization of a certain type of metric. So, not to spoil anything, but we are about to learn that certain matrices can always be guaranteed to be diagonalizable. Alright, well, let's remind ourselves what that means again. So again, a matrix is diagonalizable if it's similar to a diagonal matrix, and again, that explicitly means that A is equal to P, D, P inverse, where P isn't just some invertible matrix, and D is a diagonal matrix, a matrix whose non-zero entries only exist on its diagonal. There could be zeros on the diagonal, but anything that's non-zero has to be on the diagonal. Alright, and as we learned when we first talked about this, this is a very nice situation to be in. Similar matrices must have the same eigenvalues. A diagonal matrix is a triangular one, and thus the diagonal entries are precisely the eigenvalues for D, so they have to be the eigenvalues for A. And then furthermore, the columns of P can be demonstrated to be the associated eigenvectors. Beautiful. Okay. Now, as we saw, it turns out that not every matrix is diagonalizable. You have to have enough linearly independent eigenvectors in order to actually be diagonalizable. So, in general, it just does not happen. We saw examples, but something particularly magical happens if your matrix has the property of being symmetric. So, a matrix is symmetric precisely when it's equal to its transpose, and in this case, not only are we diagonalizable, but we can say something even stronger. So for any symmetric matrix, there is a orthogonal matrix Q and a diagonal matrix D, where we have the similarity relationship. Only, recall, orthogonal matrices are those with orthonormal columns, meaning that its transpose is in fact equal to its own inverse. Beautiful. So note, this is saying something particularly strong, that every symmetric matrix always has a full set of not just eigenvectors, there's not just n linearly independent eigenvectors, there are in fact n orthonormal eigenvectors. So it's really saying something pretty wild here, that every symmetric matrix has this property, right? At first glance, just seems to be an absolute miracle. Because it is. This is absolutely stellar that this is true. This is usually referred to as the spectral theorem, and depending on who you're talking to, so for example, our textbook, they also throw in a bunch of other things, because it turns out there's a lot more to unpack here than just simply this equation. We're not going to get super bogged down in a lot of details here. We're going to just focus in on actually doing this computation, but if you're so interested, check out what a textbook has to say about it. Now, normally with these big claims, I like to give you a little argument, a little why, a little proof as to why this is true, but this is one of those cases where this is not easy to demonstrate. This takes some finesse to get through. And I'll give you just a quick outline verbally. I didn't type anything up for it, but basically the idea is that the first thing you do is show that every symmetric matrix has only real eigenvalues, and that isn't too hard. You kind of rely on some trickery with complex eigenvalues and eigenvectors, and again into some machinery that we don't exactly have. But once you have that, then the trick is you just fix one of them, and then you get an eigenvector associated with it, and then what you do is start with that eigenvector and then extend it into a normal basis using Graham-Schmidt, and then there's some trickery you can pull to construct the matrix Q from there. There's quite a few steps to go through it. The book sort of does it, but the book kind of like sidesteps like all the details, and trust me, there are details. So, like I said, I didn't type up anything for it. If you're interested, go check it out. I'm not going to get too sweaty about it, but I do want us to go through the actual computation of D and Q. And what we're going to see here is that in this symmetric case, it's actually pretty easy to do the computation. And note, it's even better because, hey, again, you don't have the inverse here. You've just got transpose. All right. So, consider this matrix right here, notes, that's nice and symmetric. So by the spectral theorem, we know that we're going to be able to find a matrix Q and a matrix D so that A is equal to QD, Q transpose. All right. And because the Q transpose is in inverse, we know that's a similarity, so we know that the diagonal has to be the eigenvalues. So let's go ahead and compute those, which I did right here. They're -1 and 3. All right, and now we need to get that matrix Q, and as we already know, we have to have the eigenvectors as the columns in the similarity transform. However, this time around, we're going to need them to be orthonormal to make that matrix Q. So let's go and get the eigenvectors, and this time around, I don't want to get all of them. Let me just get one and work with that. So we'll subtract -1 off the diagonal, meaning I add 1 to the diagonal. And again, 2 by 2, I know I'm only going to get one equation, and it's this one right here. All right, and let me just pick a number, non-zero. And if I plug in u of 1 equals 1, I'll go ahead and get 1 -1. Beautiful. And then from my other eigenvalue of 3, subtract 3 off the diagonal, I get that equation. Again, choosing u1 equals 1 gives me that vector. And, alright, I've obtained 2 eigenvectors, and now note something special about these. They're orthogonal. As promised, the dot product of this with that does in fact equal 0. But they're not orthonormal, so I need to divide them by their length, and in this case, they both have length √2. Now, these vectors are orthonormal, and thus they will form the columns of the matrix Q that I'm looking for. And by the spectral theorem, we know that A has to equal Q dQ transpose, where Q is the columns of the eigenvectors, D is the eigenvalues in their appropriate spots. I put this one in the first column. That was the one associated with -1, so -1 needs to be in that spot right there. In the 1, 1 spot corresponding to the first column. Same thing for this. The eigenvalue 3 needs to be in the second column corresponding to that. And then over here, note, I don't have to compute P inverse to get the full diagonalization. I just need to compute Q transpose, a lot easier for computation. And equipped with that, I have orthogonally diagonalized our matrix A. And there you go. That's the story on that. Hope you liked it. See you in a review video next time.